So can you see the full screen?
Yes.
Okay. Hi, everyone. Thanks for the invitation. Today, I'm going to talk about searching for dark photon dark matter with gravitational wave detectors, O1 and beyond. I'm Fengwei Yang, and I'm a graduate student from University of Utah. And in this talk, if you have any question, please feel free to stop me, and I will try my best to answer your question. And if there is a question that I don't have an answer, I will refer it to Yue. And my talk is based on these two papers. In the first one, the first paper provides a theoretical framework of dark photon dark matter search using gravitational wave data. And in the second one, we use the LIGO O1 data to perform the dark photon dark matter search. And currently, we only include the LIGO gravitational wave data. The reason why we don't use the Virgo data will be discussed later. Okay, first of all, let me introduce dark photon dark matter to you. Although there are many observational evidence that show the existence of dark matter, we still don't know the nature of dark matter. The mass of dark matter can vary from 10 to the minus 22 electron volt to about 1 solar mass. And in the ultralight mass region, there are two popular choices. One is axion, another is dark photon. And in the ultra heavy mass region, the dark matter candidate can be a primordial black hole. And one interesting thing is that the gravitational wave detectors can probe these two extremes. And in this talk, I will focus on the ultralight mass region. And dark photon is one of the popular choices in this mass region. And dark photon is the gauge boson of the U1 gauge group. In our study, we assume there are two different gauge groups. One is U1b, baryon number. Another is U1b minus L, baryon number minus lepton number, which is different from the kinetically mixed dark photon mentioned in the previous talk. And the baryon number of an lepton is equal to the proton number plus neutron number, while B minus L is equal to the neutron number. Furthermore, dark matter is an oscillating background field if the dark matter mass is ultralight. This is because the local dark matter energy density is 0.4 GeV per cubic centimeters. To match up this local dark matter energy density, we need a large number of dark matter particles if the dark matter mass is ultralight. And in this case, there can be more than one dark matter particle within a de Broglie volume. And thus the wave property of the dark matter will become more pronounced. And since dark photon is ultralight, if dark photon plays the role of dark matter and constitute the dark matter halo in our galaxy, it will form an oscillating background field. Like the EM field, dark photon background field has dark electric field and dark magnetic field. And in later discussion, I will show you dark photon is dominantly oscillating dark electric field. And this dark electric field will drive the displacement for particles charged under dark gauge group. Since I don't have time to give you all the details of dark photon, but in general, dark photon can be massive, and there are ways to produce the correct dark matter value abundance through the non-thermal process. And now let's move to the gravitational wave experiment. There are two types of gravitational wave experiment. One is the ground-based gravitational wave experiment, such as LIGO. It is amazing how precise the LIGO gravitational wave detector can measure the relative arm length. The precision they achieve is about 1,000 of the radius of a proton at a frequency of around 100 Hertz. And LIGO has already made a big discovery of the binary black hole mergers, which open a new field named gravitational wave astronomy. And then the next question is, how can we use this fantastic experiment to perform the particle physics search? Another gravitational wave experiment is the space-based gravitational wave experiment, such as LISA. LISA is the ambitious experiment, and LISA Pathfinder is a great success. it is demonstrated that it is doable in the space. Before moving into how to use the gravitational wave detector to look for dark photon, let's first see how to use the gravitational wave detector to look for gravitational wave. LIGO is the advanced microthermal interferometer. It has two large arms perpendicular to each other, and the arm length is 4 kilometers. And there are two test masses at the same arm. And the distance between these two test masses is almost 4 kilometers. When the gravitational wave comes through, it will change the metric at the position of each test mass. And this will change the distance between the mirrors, which will also change the photon propagation time between mirrors. And thus, the interferometer pattern will show up in the photo detector. And that's how we detect the gravitational wave signal. Similarly, if dark photon dark matter background exists, it will form an oscillating background field. And the test mass at different positions will experience the forces induced by the dark photon dark matter background field differently. So after the same time interval, the test mass will, the displacements of each test mass induced by dark photon dark matter background field will be different. And this will cause the relative arm length change of the interferometer, and which will change the photon propagation time between mirrors. And thus, the interferometer pattern will also show up in the photo detector. And from the local dark matter energy density, we can estimate the amplitude of the gauge potential of dark photon dark matter, A mu 0, from this equation. And then we can calculate the local field strength of dark photon, F mu nu. Let's take the Lorentz gauge. We can obtain the electric component and the magnetic component of the dark photon dark matter background field. And we find that the electric component, the E field, is proportional to the time derivative of the gauge potential, while the B field is proportional to the spatial derivative of the gauge potential. And there is an additional factor showing in the B field, which is the velocity of the dark photon dark matter. And the typical velocity of the dark photon dark matter is the visual velocity of the dark matter halo in our galaxy, which is about 10 to the minus 3 speed of light. In the natural unit, C is set to 1, so the B field is 3 order magnitude smaller than the E field. And that's why we only consider the dark electric field in our study. Okay, after obtaining the local field strength of dark photon dark matter, we can calculate the forces induced by the dark photon dark matter background field on the test mass, which is given by this equation. And there are three components in this equation. The first component is the dark photon coupling. And the second component is the charge mass ratio of the test mass. And the third component is the dark electric field. And after obtaining the acceleration of each test mass, we can project it along the arm direction, which will give you A parallel. And take the time integral of A parallel twice, we can obtain the displacement of each test mass. And after obtaining the displacement of each test mass, we can calculate the relative arm length change of the interferometer, delta L, as a function of time t, and which is given by this equation. Delta L is defined by the relative arm length change of the X arm minus the relative arm length change of the Y arm. And by averaging on directions of the acceleration and momentum vectors of the dark photon, we can obtain these two formulas, which describe the maximum value of the relative arm length change of the interferometer for LIGO and LISA. And from this result, we find that the relative arm length change is proportional to the typical velocity of the dark photon dark matter. And if the visual velocity of dark matter is 0, the dark photon dark matter background field will give the same force to all test mass. And thus the test mass will move the same way. So in this case, the gravitational detectors cannot detect the dark photon dark matter signal. Okay, now let me show you some properties of the dark photon dark matter signal. First, the signal is almost monochromatic. The frequency of the signal is determined by the mass of dark photon, MA, which is a constant. And second, the signal has a very long coherence time. That means the intrinsic wave of the signal is very small and is determined by the dark matter velocity dispersion. And the dark matter velocity dispersion is determined by the gravitational potential of our galaxy. And by using these two properties, we can do a bomb hunting search of the signal in the frequency space. And this bomb hunting search can be further refined as a detailed template search if we know the shape of the signal, assuming, for example, assuming the Boltzmann distribution for the dark matter velocity. And that's what we are doing now. And the third property of the dark photon dark matter signal is that it has a very long coherence distance. The coherence distance is proportional to the inverse of the momentum of dark photon. And for 100 Hertz signal, the coherence distance is about 3 × 10⁹ meters, which is much larger than the radius of the Earth. That means within the coherent distance, the gravitational detectors on Earth will experience almost the same dark photon dark matter background field. As I mentioned before, LIGO is the ground-based gravitational detectors, and there are two LIGO detectors on Earth. One is in Hanford, another is in Livingston. And the distance between these two detectors is about 3,000 kilometers, which is much smaller than the coherent distance of the dark photon dark matter background field. And so the signal induced by the dark photon dark matter background field on these two detectors are almost the same. So the signals are correlated. That means the signals from these two detectors are correlated. And we can use the correlation between these two detectors to suppress the noise in the analysis. And here one may wonder, including the Virgo will help the search. However, the answer is not much. This is because the Virgo is not very well aligned with these two LIGO detectors. The correlation for Virgo and LIGO is not so significant. And now let's see how to calculate the sensitivity to dark photon dark matter signal of gravitational wave detectors. First, we will estimate the sensitivity in terms of gravitational wave stream. And then we will translate the sensitivity of gravitational wave stream to the sensitivity of the relative arm length change. The gravitational wave signal is defined by the one-sided Paul spectrum function SGW, which is proportional to the differential energy density distribution function omega GW. And omega GW is defined by this equation. And it is proportional to d rho GW over df, where rho GW is the energy density carried by the gravitational wave. And under the gravitational wave plane wave assumption, one can simply rewrite omega GW as the ratio of the energy density carried by a gravitational wave plane wave to the intrinsic wave of the signal. And of course, one can use, if one knows the detailed shape of the signal, one can do a template search. And one can expect a better detection sensitivity. And that is what we are doing now. And after some calculation, we can obtain the sensitivity of strain for a pair of gravitational detectors, and which is given by this equation. Here, SNR is the signal to noise ratio. H0 is the amplitude of the gravitational wave stream. Gamma is the overlap reduction function, which describes the correlation of the signal between two gravitational wave detectors. And T is the observational time. P1 and P2 is the one-sided Paul spectrum of the noise for two gravitational wave detectors. and the delta F is the intrinsic width of the signal. And at the same time, the gravitational wave stream is proportional to the relative arm length change up to an order of 1 number. So we can directly translate the sensitivity of the gravitational wave stream to the sensitivity of the relative arm length change. And in the previous slide, I have already given the formula of the relative arm length change in terms of the dark photon dark matter parameters, such as mass and coupling. And thus, we can use this equation to translate the sensitivity of relative arm length change to the sensitivity of the dark photon dark matter parameters. And here, let me show you a sensitivity plot. Here, the x-axis is the frequency of the signal corresponding to the dark photon dark matter mass. And the y-axis is the dark photon dark matter coupling strength square under U1B gauge rule. Here, the green curves show you the 2 sigma constraint from the laser lunar ranging experiment. The blue curves show you the 2 sigma constraint from the equivalent principle test by Edwards group using a torsion balance. And here, the red dashed curve and red solid curves show you the expected 5 sigma and 2 sigma constraint of the advanced LIGO design sensitivities using 2 years 100 lifetime run data. Similarly, the brown curve shows you the constraint, expected constraint from LISA. And from this plot, we find that the gravitational experiment can probe the unexplored parameter region of dark photon dark matter. And since LIGO is very interested in our proposal, we use the LIGO 01 data to perform the dark photon dark matter search. And here I list some details in the analysis. Since we are looking for the signal in the frequency space, so we need to take the Fourier transform of the gravitational wave time stream data. And we divided the time series into many small time segments with duration of 1,800 seconds, which is optimized for a signal at the frequency of around 500 Hertz. And we perform the frequency cut by removing the no noise beams and their neighbor beams. And since we are looking for the signal within 10 to 2000 Hertz frequency band, rather impose the signal to noise ratio, so we need to consider the look elsewhere effect. Rather than impose the signal to noise ratio to 3, we impose the signal to noise ratio to 5.8. to obtain the 1% false alarm probability after including these trial factors. To deal with the non-Gaussian noise, we use the frequency lags to calculate the cost correlation of the signal between 2 detectors. That means rather than using the same frequency bins of 2 detectors to calculate the cost correlation, we offset the frequency bins for 1 detector and then calculate the cost correlation. By using frequency lags, we can remove the single interferometer artifact and the ball band correlated artifact. And here, the result of the distribution of the real part of the signal to noise ratio is given by this plot. And the result is consistent with the Gaussian distribution, which is given by this green curve. And our search method is so efficient that we find out the known continuous wave hardware injection, which is highlighted by this blue circle. Okay, now let me show you the 01 result. Here, this plot gives you the 95% confidence level upper limit of the dark photon dark matter coupling strength under U1B. And the coordinate of this plot is similar to the coordinates of the previous sensitivity plot. And here the red curves show you the actual upper limit by using the measured signal to noise ratio with 0.5 millihertz binning. And the fluctuation on this red curve is from the random noise. And the green curve is the expected upper limit by using the average signal to noise ratio equals to 0. And both red curve and green curve are using the fixed beam size. However, for different frequency, the optimal beam size should be different. If use the optimal beam size, one should obtain the blue curve. And the outliers on this blue curve are the no power line of the gravitational detector. The dashed curve gives you the upper limit from the equivalent principle test by Edwards group. By comparing the dashed curve and the blue solid curve, we find that the O1 result has already improved on the existing limit at the mass region of around 4 × 10⁻13 electron volt. And future searches on more sensitive data will probe the unexplored parameter region. And this magenta curve shows you the expected upper limit from the advanced LIGO design sensitivity using 2 years 100 lifetime run data. Okay, for the rest of my talk, I will briefly talk about what we are doing now. As I mentioned before, we are doing a bomb hunting search as a guideline. And now we want to study the detailed feature of the signal. So we need to go beyond the coherence time, and we need to model the dark photon dark matter background first. And here we use the sinusoidal function to describe the wave function for each dark photon. Here, omega I is the frequency of each dark photon, ki is the momentum of each dark photon, and phi I is the random phase. And here, the frequency and momentum of dark photon follows the Boltzmann distribution. And since we are focusing on the ultralight dark photon, the wave function of each dark photon will overlap with each other. And so we can just sum up all the wave function of dark photon to obtain the total dark photon dark matter background field, A total. And by using the simulated data, we can reproduce the coherence time and coherence length of dark photon dark matter background field, which are given by these two plots. And then we we inject the simulated signal into LIGO simulation package and obtain the signal to noise ratio in the frequency space. And here the x-axis is the frequency, while the y-axis is the signal to noise ratio. As you can see, there is a narrow peak showing at the frequency of around 70.71 Hertz, which is exactly what we set in our simulation. And by choosing these parameters, we can obtain the signal to noise ratio value is about -8. Here, the minus sign is coming from the fact that the two LIGO detectors are anti-aligned. And in our simulation, we also include the Earth rotation effect. If there is one dark photon dark matter plane wave, one would expect the signal in the frequency space should be a peak. However, after including Earth rotation effect, this one peak is split into 5 peaks. And the frequency difference between two neighboring peaks is the Earth rotation frequency. And further, we divide the analytical formula to describe the Earth rotation effect, which is given by this equation. Here, omega E is the Earth rotation frequency. Omega I is the frequency of each dark photon. And the term in this bracket tells us how the Earth rotation effect modulate the frequency of the signal. And if one use more than one dark photon dark matter to constitute the dark photon dark matter background field, one will obtain the frequency power spectrum look like this. It has a spiky feature. This is because for each frequency beam, there are many dark photon particle contributing on the same frequency. And since each dark photon has different phase, this will cause the interference at that frequency beam. And here in this plot, the red curve is the numerical results obtained from the simulation data, while the blue dashed curve are the analytical result obtained from the analytical formula. And these two curves are well fitted. That means the analytical understanding of the power spectrum matches very well with the numerical result. Okay, in conclusion, the application of gravitational experiments can be extended. The gravitational experiment is particularly sensitive to gravity displacement. At the same time, coherently oscillating dark photon dark matter generates such displacement. So the gravitational experiment can be used as a dark matter direct detection experiment. Second, the analysis of dark photon dark matter search is straightforward. It is very similar to stochastic gravitational wave searches. And the advantages of this search is that it has a better coherence between separated interferometers than stochastic gravitational wave background. And third, the sensitivity of this search can be extraordinary. We find that O1 data has already beaten existing experimental constraints, and LIGO can achieve phi sigma discovery at unexplored parameter regions. And once measured, great amount of dark matter information can be extracted. That's all of my talk. Thanks.
Thank you very much. So does anybody have any questions?
Hi, can you hear me?
Yes.
Sorry. So I have a couple of curiosities. Thanks for the nice talk by the way. So your analysis considered dark matter from the standard Milky Way halo. Am I correct?
Sorry, from the
the source of the source of dark matter in this case is the standard galactic halo. Is it?
Yes, it formed our galaxy halo.
Okay. So have you considered, for example, if there are dark matter from other sources, is it, I mean, what kind of sensitivities you get, for example, like some other boosted dark matter or warm dark matter component passing through?
For this sensitivity curve, we are assuming the dark photon, the polarization vector of the dark photon background field is isotropically distributed.
Okay.
Yeah.
Okay. Thank you.
You're welcome.
Can I ask a question?
Yes, sure.
For the epsilon parameter, the coupling between the dark photon and the baryon, is this coupling universal to baryons?
Baryon. Do you mean pion?
Baryon.
Oh, baryon. Universal. Yes, since it is proportional to the baryon number or baryon number minus lepton number. So since the mirror is composed of the silicon, so the mirror will experience the forces induced by dark photon dark matter.
If this coupling is universal, why Atwash experiment can put a constraint on this? Because it do not violate equivalence principle.
Maybe you can comment this question.
Yeah, sorry. Let me very quickly answer this question. So first of all, it is very clear that if we assume the dark photon is the gauge boson of U1 B mass L, that will be constrained by the Atwater experiment, because the mass is not directly related to the mass is not directly proportional to the neutron number, right? So for the U1B, that's actually a good question. I'm not 100% sure about the answer, but my very naive guess on that is because the Atwater experiment somehow is rotating on a turning table, and that will somehow distinguish and with different choices of elements, they may have a sensitivity to the U1B. I'm not 100% sure about that answer.
Okay, a related question. Because for the LIGO detection, the oscillation frequency is about 100 Hertz, so which corresponding to 10 millisecond. But the integration time in Atwater is very long. It's much longer than this. The effect should already be washed out, be averaged out. Is
yeah.
that
so the Atwater experiment that we are coding here is the constraint here doesn't rely on the assumption that the dark photon is dark matter. So this is basically just the extra fifth force between the test object and the Earth. So in that case, you just so because the experiment is operating on a turning table, and the signal that they are looking for is still a finite frequency signal. It's not a pure constant. I don't know whether that answers your question.
I'm not sure if I understand the answer. Yeah, but
yeah. So the Atwater experiment doesn't rely on the fact that dark photon is dark matter. So there isn't a intrinsic oscillation frequency that the dark matter the LIGO experiment has this 100 Hertz, which is the oscillation frequency of the dark photon dark matter particle itself. But for the Atwater experiment, if it's just a fifth force experiment, it's a constant force.
So it doesn't matter if it is a dark photon or not, right?
That's right. In principle, this can also probe the fifth force like a scalar.
So this may be where I'm confused. So how do these two experiments are related? So if it doesn't matter if it's a dark photon or not.
So if you have a dark photon being dark matter, then it will be an oscillating background field. But if the dark photon exists at all in the particle spectrum, that can be a force mediator, and that will mediate the additional force beyond gravity between the test object and the Earth. And that is how the Atwater experiment is testing the existence of dark photon. It doesn't rely on the fact that dark photon to be the assumption that dark photon to be the dark matter.
Okay, thank you.
More questions? Looks like none. So thank you again, Fengwei, and everybody, please be back on Thursday for our next session. So thanks and bye.
Bye.
Thanks.